Hi, I want to talk about the second and third laws of thermodynamics. Mostly, though, the second law of thermodynamics. And this is just a very brief toe dip into what is a topic that could very easily span several books. Now, the second law of thermodynamics, like the first law of thermodynamics, was something that was first worked out in a lab trying to explain the behavior of heat engines. And with the first law, we talk about energy balance and the idea of energy conservation. Well, with the second law, as it relates to heat engines, it was observed that it is impossible to perfectly convert heat into work. You can convert work into heat, those are totally equivalent, but you can't take some energy out of a high temperature source and convert 100% of that energy into work. And the theorists jumped in a little bit later and added a little addendum that says, unless you get to absolute zero. So above 0 Kelvin, it's impossible to perfectly turn heat into work. So typically when we talk about engines, we talk about the process of efficiency. And efficiency, by definition, is the amount of work that we get out of an engine divided by the amount of heat that goes into an engine. Now, from the first law of thermodynamics, the amount of work that we get out would be equal to the amount of heat that comes out of our hot source minus the amount of exhaust heat that's going into our cold source. So that also means we could describe our efficiency as 1 minus the exhaust heat divided by the amount of heat that goes into that engine. And it turns out, too, from some other consequences stemming from the second definition of the second law, there's a maximum possible efficiency that's based off a type of engine process called the Carnot engine. And a Carnot engine has a theoretical maximum efficiency equal to 1 minus the thermodynamic temperature of the cold reservoir divided by the thermodynamic temperature of the hot reservoir. So that's where this absolute zero wiggle room comes into play. If you could have a cold source at absolute zero, then conceivably you could have 100% efficiency. Now, I'll jump down just to talk about the third law because in most introductory physics books, about as much as you'd mention with the third law is to say that absolute zero can be approached, but you can never reach absolute zero in a finite series of cooling steps. So what this means in practical terms, the equation, the heat is equal to the amount of something times the specific heat times the change in temperature, that equation will break as your temperature starts getting close to absolute zero. Now, let's go back to the second law. There is another type of state function in thermodynamics. There's several. Energy is the first state function we talked about, and energy is related to the thermodynamic temperature. Another state function is called entropy. And entropy, in a way, is a measure of the order or disorder that you would see in a configuration of energy. So, in general, in terms of entropy, if we have a closed system, so that means there's no external inputs or outputs, entropy increases during an irreversible process. And entropy would remain constant after a reversible process if you undergo the reversible process and completely undo it. That would be a constant entropy situation. So to write this as an equation, the change in entropy of a system that's closed is always going to be greater than or equal to 0. Now, it doesn't mean we can't lower entropy. You can lower the entropy of a system by raising entropy as part of the larger world, but that idea of closed means we've cut that system off from the larger world.